There is a refrigerator that runs on noise, not metaphorically. You feed sound into a sealed tube, and the sound itself pumps heat from one end to the other. It has no compressor, no refrigerant, and no seals to fail, and a version of it was flown and operated aboard the space shuttle in 1992. Two honest things before we go a step further, because I'm not going to spring either on you halfway through. The first is that the $10 version demonstrates the effect. It genuinely produces a measurable temperature difference, and it is one of the most satisfying things you can build on a bench, and it is not going to chill a drink. Serious thermoacoustic coolers use pressurized helium and precisely calculated geometry, and I will explain exactly why in a few minutes. The second is the noise. This machine works by making sound, and a working one is loud enough that hearing protection is not optional. That is not a footnote. It is the single biggest practical reason this technology has not appeared in your kitchen. And one more thing, which I will come back to at the end. There is a reason serious institutions keep funding this, despite it being less efficient than the compressor in your fridge. It has nothing to do with efficiency at all. When you see what that reason is, the whole field makes sense. Let me start with the idea underneath it, because almost nobody has had this explained, and it is genuinely strange. Every sound you have ever heard was also a temperature wave. Sound is not a substance moving through air. Sound is a pressure wave, meaning a pattern of squeezing and stretching traveling through a gas. When a speaker cone pushes forward, it compresses the air in front of it, and when it pulls back, it stretches it, and that pattern races away from the speaker at the speed of sound. Now think about what happens to a gas when you squeeze it. It heats up, release it, and it cools. That is the same reason a bicycle pump gets warm in your hand, and an aerosol can get cold. So every compression in a sound wave is very slightly hotter than the surrounding air, and every rarefaction is very slightly cooler. That is true of every sound that has ever existed. Your voice, traffic, music. And every gas parcel in that stack is doing the same thing, thousands of times a second, all in step, each one handing heat to its neighbor like a bucket chain. The result is that heat is pumped steadily from one end of the stack to the other, against the temperature gradient, which is precisely what a refrigerator does. One end gets cold, the other gets hot. And the only moving part in the entire device is the speaker cone. Now let me deal with the doubt some of you are sitting with, because it is the right question. You are thinking that if sound could genuinely make cold, somebody would be selling one, and the fact that nobody is means it cannot really work at any useful scale. That objection is fair, and there are two answers. The first is that it does work, and it has been demonstrated at a level that leaves no argument. A thermoacoustic refrigerator was carried aboard a space shuttle mission in 1992 and operated in orbit. NASA does not fly experiments that do not function. The second is that it is genuinely in commercial use, just not where you would look for it. Thermoacoustic coolers are used for cryogenics, meaning producing extremely low temperatures for cooling scientific instruments and liquefying gases. In that world, a cooling device with almost no moving parts near the cold end is enormously valuable, because vibration ruins sensitive measurements, and mechanical failure at cryogenic temperatures is a serious problem. There have also been high-profile demonstration builds, including an ice cream cabinet developed with university researchers as a proof of concept, specifically to show that the technology could hold food freezing temperatures. So the question is not whether it works, it is why it stays in those niches, and that answer comes later in this video. Now, where this came from, because the history is better than the technology deserves. The effect that underlies all of this was noticed as early as 1777, when an English scientist named Byron Higgins reported that a flame placed inside a tube would produce a musical note. It became known as the singing flame, and for well over a century it was a demonstration nobody could properly explain. Then, in 1859, a Dutch physicist named Peter Ricke made it repeatable by placing a heated wire gauze inside a vertical open tube and producing a loud, sustained tone. That arrangement is still called a Ricke tube, and it is still used in physics teaching today. But notice what all of those had in common. They were heat going in and sound coming out. The mathematics that finally described what the gas was actually doing arrived in the 1970s from a Swiss physicist named Nicholas Roth, and that is what turned a party trick into an engineering discipline. And once you have the mathematics, you can run the machine backwards. That is exactly what happened at Los Alamos National Laboratory, where researchers, including John Wheatley and Greg Swift, built thermoacoustics into a serious field through the 1980s and 1990s. They worked on both directions, heat in and sound out, which is a thermoacoustic engine, and sound in and cold out, which is what we are talking about. There is a distinction from that work worth knowing, because it separates the demonstration from the serious machine. The simple version, and the one you will build, is a standing wave device. The sound bounces back and forth inside the closed tube and forms a stationary pattern, and the gas parcels in the stack move slightly out of step with the pressure changes around them. That imperfect timing is deliberate. It is what makes the heat transfer happen at all, And it is also the limitation because a portion of the heat moves at the wrong moment in the cycle and is simply wasted. The advanced version is a traveling wave device, built as a loop rather than a straight tube, so the sound circulates around the circuit instead of reflecting back on itself. In that geometry, the pressure and the motion of the gas can be brought properly into phase, and the gas executes something extremely close to an ideal thermodynamic cycle. And that is where the serious efficiency figures come from, and it is a considerably harder build. So the honest guidance for anybody at a bench is that a straight tube demonstrates the effect beautifully and cheaply, and a loop is where the performance lives. The same laboratory later produced a thermoacoustic engine reaching around 30% thermal efficiency, published in Nature in 1999, which is genuinely comparable to a petrol engine from a device with no pistons. So this is not a fringe pursuit. It is a national laboratory field with decades of work behind it. Now let me build one, because the demonstration version is genuinely achievable. You need 4 things. A resonator, which is a tube closed at one end. Length matters because you want the tube to ring at the frequency you are driving it with, exactly like an organ pipe. A clear acrylic or glass tube is ideal because you can see the stack and a length of pipe works. A speaker mounted sealing one end of that tube. This is your compressor, and it is the only moving part. A small driver is fine for a demonstration, and a stronger one gives you a bigger effect. A stack, which is the heart of the machine. Fine mesh, a roll of thin plastic film with fishing line spacers, or a stack of thin plates. What you want is a great deal of surface area with narrow gaps for the gas to move through, positioned at the right point along the tube. The spacing in that stack is not arbitrary, and it is worth understanding because it explains why a random handful of wire wool disappoints. There is a distance from any solid surface within which a gas can exchange heat with it during one cycle of the sound wave. Engineers call it the thermal penetration depth, and it depends on the gas and on the frequency you are running at. Higher frequency means a shorter distance because there is less time in each cycle for heat to travel. Your gaps want to be somewhere in the region of a few times that depth. Too narrow and the gas cannot move freely, so you choke the flow and add friction losses. Too wide and the gas in the middle of the gap never gets close enough to the surface to exchange anything, so most of your working fluid is doing nothing at all. That is why serious stacks are made of thin parallel plates at a calculated spacing rather than a random porous lump. For a bench build, a roll of thin plastic sheet with fishing line laid between the layers as spacers is the classic homemade solution, because it gives you parallel channels at a spacing you chose rather than a spacing you got by accident. And it is why 2 builds using the same tube, the same speaker, and the same frequency can produce wildly different results. The stack is the machine, and everything else is supporting it. And a signal source, meaning a tone generator app on your phone and a small amplifier, so you can drive the speaker at a specific frequency and sweep it to find the tube's resonance. The whole thing lands somewhere around $10 to $40, depending on what you salvage. Now, the 2 details that decide whether it works. The first is finding resonance. Sweep the frequency slowly and listen. At most frequencies, the tube will simply reproduce the tone. At one particular frequency, it will suddenly get much louder and the sound will change character, and that is the tube ringing at its natural note. That is where you leave it, because that is where the sound wave inside is strongest. The second is stack position, and this is where every failed build goes wrong. The stack has to sit at a specific region along the tube, where the gas is both moving and experiencing pressure change. Put it in the wrong place and nothing happens at all, and people conclude the effect is fake. The practical approach is to build the stack so you can slide it, run the tube at resonance, and move the stack while watching a thermometer or a thermocouple at each end. You will find the position where the temperature difference appears, and it is often narrower than people expect. With a modest setup, you should see a few degrees of difference across the stack within a minute or 2 of running, not frost. A few degrees, and one end genuinely cooler than the other, produced by nothing but sound. That is the demonstration, and it is a real result. Now the honest reason it stops there, and this is the arithmetic I promised you. 2 things limit a home-built thermoacoustic cooler, and both are about the gas. The first is pressure. Acoustic power in a gas depends on the density of that gas, and air at atmospheric pressure is not dense. Serious thermoacoustic devices operate at many times atmospheric pressure, precisely to get more acoustic power into the same volume. The second is what the gas is. Serious devices use helium rather than air, because sound travels faster in helium, and it carries acoustic power far more effectively, and it has thermal properties that suit the process better. Put those together, and a laboratory device running pressurized helium is working in a completely different regime from your acrylic tube full of ordinary air. That is why the gap between a demonstration and a freezer is so wide, and it is not a matter of building yours slightly better. It is a matter of pressure vessels and inert gas handling, And I want to say this clearly. Do not pressurize a home-built resonator. A sealed tube under pressure with a speaker glued into one end is not a project. It is an accident. And the demonstration version at atmospheric pressure is genuinely worth building on its own terms. Now, the noise, because this is the practical barrier that keeps this technology out of ordinary life. The working fluid is sound, not a metaphor. The thing doing the cooling is a very intense sound wave inside that tube. Serious devices operate at sound levels that would be genuinely damaging if you were exposed to them directly, which is why they are enclosed and why the tube is sealed. Well-designed machines contain that sound inside the resonator and are reasonably quiet on the outside. Your demonstration build will not be. An open bench setup driving a tube at resonance is loud, and it is loud at a single piercing frequency, which is the most unpleasant kind. So wear hearing protection. Run it in short bursts rather than leaving it going, and do not do this in a room with other people who did not volunteer. Now the honest comparison, because this video is about a refrigerator and I owe you a straight answer. The compressor in your kitchen fridge is a heat pump, and modern vapor compression achieves a coefficient of performance well above 1, meaning it moves several units of heat for each unit of electricity. Thermoacoustic coolers are less efficient than that. The gap has narrowed over decades of research, and it is still a gap. So on pure efficiency, the machine in your kitchen wins, and it wins comfortably. Which brings me to the thing I promised at the start, and it is the reason serious institutions keep funding this anyway. Reliability. Almost everything that fails in a machine fails at a moving interface. Bearings wear, seals harden and leak, pistons scuff their cylinders, valves stick, lubricant degrades. Every one of those is a maintenance visit or a breakdown. A thermoacoustic cooler has one moving part, which is a loudspeaker diaphragm on a suspension, and that is a component with no rubbing surfaces and no seals to lose their charge. Remove all the rest, and the failure modes that remain are measured in decades. Now think about where that matters more than efficiency. On a spacecraft, where nobody can service anything and a single mechanical failure ends the mission. In cryogenic laboratory equipment, where you need extreme cold in a compact package with no consumables and no vibration. In remote installations that nobody visits. And in any application where the refrigerant itself is the problem. That last one deserves its own moment because it is the strongest argument this technology has. The refrigeration industry spent the 20th century cycling through working fluids. The early ones were toxic gases, and people died from leaks in their own homes, which is precisely why Einstein and Szilard patented a refrigerator with no seals in 1930. Then came the chlorofluorocarbons, which were safe to breathe and turned out to be destroying the ozone layer. Then came their replacements, which turned out to be extremely powerful greenhouse gases. Every generation of refrigerant has been a compromise that a later generation had to solve. A thermoacoustic cooler runs on an inert gas, usually helium, which is non-toxic, non-flammable, and does no environmental harm if it escapes. So the argument is not that this is more efficient. It plainly is not. The argument is that it is a cooling technology with essentially no failure modes and no refrigerant problem at all. And those two properties are worth a great deal in the places where they matter. Now the honest limits, all of them. The first is efficiency, which I have given you and will not repeat. The second is power density. Thermoacoustic devices are bulky for the cooling they deliver, which is fine for a laboratory instrument and awkward for a domestic appliance. The third is the noise, which is the practical killer for consumer use. A kitchen appliance that requires acoustic containment is a harder engineering problem than one that does not. The fourth is that the demonstration version genuinely is only a demonstration. A few degrees across a stack is a real result, and it is not refrigeration, and anybody showing you a bench tube freezing water is showing you something other than an acrylic pipe full of air. The fifth is that the working gas matters enormously, and that puts serious performance behind a pressure vessel and a supply of helium, neither of which belongs in a home build. And the sixth is heat exchangers, which is the unglamorous part where most of the real engineering effort in this field actually goes. Getting heat into and out of the gas efficiently at each end of the stack is harder than making the sound wave, and it is what separates a laboratory device from a toy. That deserves a proper explanation because it is the part nobody films. Your stack is pumping heat from one end to the other beautifully, but that heat has to arrive from somewhere and go somewhere, or the whole thing simply reaches a small temperature difference and stalls. At the cold end, you need something that collects heat from whatever you are trying to cool and delivers it into the oscillating gas. At the hot end, you need something that takes heat out of the gas and dumps it into the room. Both of those are heat exchangers, and they have to work with a gas that is not flowing steadily past them, but oscillating back and forth over a very short distance, which is a genuinely awkward engineering problem and quite unlike designing a car radiator. Get them wrong, and your stack pumps heat efficiently into a bottleneck. The ends saturate, and the machine looks far worse than the physics says it should. That is why laboratory devices have carefully engineered fin structures at each end of the stack, and why a bench demonstration with bare tube ends produces a few degrees rather than genuine cooling. The sound wave is the glamorous part. The heat exchangers are where the performance actually lives. So who is this actually for? If you want to understand how heat pumps work, this is one of the best demonstrations available because there is nothing hidden. You can see the stack, there is no sealed system, no refrigerant, and no black box. The physics is visible. If you are teaching, or you have children who ask why things work, this is genuinely excellent because the result is surprising and the explanation is complete. If you want to cool something, buy a fridge. And if you are watching this because you saw a claim that sound can replace air conditioning in your house, the honest answer is that it cannot today, and that the people working on it are aiming at spacecraft, instruments, and applications where refrigerants are unacceptable, rather than at your kitchen. So this week, if you want to actually try it, here's where I would start. First, before building anything, hear the effect running in the other direction. A Reka tube, which is a vertical pipe with a heated gauze inside it, is the cheapest demonstration in this entire subject, and it produces a startling amount of noise from a piece of pipe and a torch. Second, if you build the cooler, buy or borrow a thermocouple thermometer before you build anything else. You cannot tune this by feel because the effect starts small, and without a way to read both ends, you will move the stack around blindly and give up. Third, make the stack slidable from the very beginning. Every build that works has that feature, and every build that fails did not. Fourth, use a tone generator app and sweep slowly. Resonance is narrow and it is obvious when you hit it. And fifth, put hearing protection on the bench next to the tube before you switch anything on, rather than after. Tell me in the comments whether you have ever seen a thermoacoustic device running. And if you build one, tell me what temperature difference you actually measured and where your stack ended up. I read every one of these, and that stack position is the whole trick, and almost nobody publishes theirs. Here's the thing worth keeping from all of it. In 1777, somebody noticed that a flame in a tube made a musical note, and for nearly 200 years, that observation sat in physics demonstrations with no purpose and no proper explanation. Then somebody worked out the mathematics, realized the process ran in both directions, and built a refrigerator whose only moving part is a loudspeaker. The physics did not change in those 2 centuries. What changed is that somebody finally asked what the singing flame was actually doing and found a working thermodynamic cycle hiding inside a party trick. And the version of it that flew on a space shuttle in 1992 was not chosen because it was efficient. It was chosen because there was almost nothing in it that could break, in an orbit that is worth more than efficiency will ever be, which is worth remembering the next time something is dismissed for being less efficient than the alternative. Efficiency is one axis. It is not the only one, and it is not always the one that decides.